Hi. People don't like to talk about negative things like failures, but today that is the one and only thing we are going to do, talk about failure. In the last lectures, we talked about Murphy's law pertaining to maintenance. Again, I will be introducing Murphy to define the concept of failure. Murphy in his laws states, if an equipment can fail, it will fail. Anything that can go wrong will go wrong. You can't stop it, you understand. And most important, failure will usually occur at the most inconvenient time. Remember the word most inconvenient time. I am getting late for the job. I want to start my car doesn't start. I get irritated. I do some more errors while starting the car. That's typical Murphy law. Now let us look what is the relationship between reliability. The lectures I discuss. I introduced you the reliability in my previous lecture. Failure and reliability are very closely related to each other. Reliability or unreliability is a sense gives the definition of failure. If something is unreliable means there is a impending concept of failure around it. So failure and reliability are very closely related to each other. Reliability is nothing, as you saw in the last lecture, is the probability of no failure over a specified time interval and a given working condition or a specified condition. But what is failure? Failure is nothing. It can be defined in different words. If you think in the past, 100 years ago, something broke, we said it has failed. So failure notion was associated with fractures, something broken. And you look at this example, this road is, there is a crack in the road. We said that material has failed. But with advances in technology, when I want to start my car doesn't start, means there is a loss of function. So failure was associated, there is nothing is broken, only my car is not starting. So it was associated with loss of function. One more example, when I want a water from a tap, it doesn't give me water. Means there is no function. There is a loss of function. That's a good example. Second one, maybe system is available. My car was working. Everything was okay. But when I want to start, it is not starting. Means when I want to start the car, it doesn't start. Gives me a feeling of loss of function when I wanted the function. But good example is our alarm in our houses. Usually we'll see many times alarm doesn't work when we want it to work. So all safety systems or all systems that should work on demands are categorized under loss of function when you want the function. That's a good example. Let's summarize. Let's define failure. What is the definition? So failure is defined as the termination of the ability of an item to perform a required function. And the concept of when it is want is hidden inside. And this is the standard definition from the book of standard. I will be now introducing you another word called fault. And often we mix these two concepts, fault and failure. Fault is nothing but it is a state of an item characterized by inability to perform a required function. So fault is an state. This is an example of fault, faulty deck. Whereas failure is an event. And failure is defined as the termination of the ability of an item to perform a required function. So I am repeating, fault is a concept of a state. The item is in a faulty state, whereas failure gives you an event, failure event. So fault is a state where failure is an event. We should remember it. And this is an example of failure that there is no power supply, the event. It indicates the event that there is no, something has happened and there is no power supply. But computer is in a faulty state because there is no working state. Now I'll introduce you. We haven't seen the fault and the failure. Now we'll talk about failure mode. Failure mode is a description. Some typical failure modes can be described by premature operation. Like let's say I want to close a water tap, but still water is coming out. That's a typical example of a valve failure. So some of the examples like premature operation, Failure to operate at the prescribed time. I want to start something, it doesn't start. Failure to cease operation at the prescribed time. I want to close the tap water, but it's still water is coming. And or sometime you want to have very less water coming from the tap, still it is coming. So typically, if I take another example like a valve, when I want to close it, it's not closing. That's one example. When I want to open a valve, it's not opening, or it is only opening halfway. That's a good example of some of the example of failure mode. We'll be looking now at failure causes. Why do system fail? And it can be broadly classified into three categories: failure due to design problems, design issue, failure due to the manufacturing issues, and failure due to bad use or bad applications. Looking into the design. Design is one of the most important reason for that system to fail. Actually, in fact, it can be attributed almost more than 50% of the causes. And lot of research has been done, lot of study has been done. How can we improve the design so that system don't fail? In design, we foresee the future. We foresee the application of system or an item in an environment, but that environment is not the reality. It is operated in a different environment, and then system do fail. One example I remember, when a Swedish company wanted to introduce trucks in India. These trucks were very successful on Swedish road, but they were not at all suitable for Indian road, and they failed because designer he didn't visualize the road condition. They didn't visualize the road condition, leading to premature failure. So these are very, very important points. This design, you have to foresee the future, you have to foresee the operating condition, you have to foresee the maintenance people's skill, you have to understand also the people who are going to use it. They are very, very complex issues, but it happens. Then also many times designer understand everything, but he introduces something, some poor material. Let's say like an example of telephones. When you buy a mobile telephone, they are tested often many times for drop test. Like if you drop a telephone from your hand, sometimes your glasses do break. But in reality, telephone manufacturers, they test it. They drop maybe 1,000 times in a controlled conditions in different angle, even though they miss some particular angle that you will drop the telephone. So if you drop the telephone by that angle, it will fail. So these are the unplanned. People have not thought about those weaknesses, and they get into the product and they lead to failures. So weaknesses in design can be lead to some failures and all. But when the design is done, everything is perfectly calculated, it goes for manufacturing. There are some due to the machine problem, manufacturing system problem. Like if your machining tools are not perfect, it will lead to manufacturing problem. There will be tolerances will not be correct, or simply you are not able to welder because designer, again, see how related manufacturing is to design. Designer could not visualize that welding at that particular point is almost difficult, very difficult. You cannot do a perfect welding, leading to problem in manufacturing. You couldn't welder it in right way, leading to failure in the during application. So manufacturing is also very important. So therefore manufacturing and designer groups should work together. That's one very, very important thing. And applications, as we know, if I'm a good driver, my car will last longer. If I'm a poor driver, I will destroy the things. I'll destroy the gearboxes, I'll destroy the clutches, brakes very fast. So this is a very, very important thing. But even more important, I talked about misuse, is aging. With the age, system to degrade and fail, and many times even mishandling. If I buy a component machine, during transport it got mishandled and fails. Different type of stresses are brought to the system, and they are not good for the health of the machine or system. It may fail. So these are some of the causes of failure. While summarizing, I will tell that every item is unreliable in the sense that it may fail sooner or later, even with the best design, best construction and maintenance and operation, because most of the systems are designed for a particular period of time, 5 years, 10 years, 20 years, or sometimes even 40 years. But situation do change in 40 years. We have not visualized all the conditions. One of the good example is climate changes. Nobody knows what is going to happen in 5 years. So even they have the best design, it is likely to fail. And we should be ready for these situations. Failure causes are useful information in the prevention of failures or their recurrences. Every failure is a learning step for us. We learn a lot from the failure so that we can design future system with all these precautions or all these the safe valves, safety guards, etc. so that failure will not be encountered. So this is very important topic to understanding the failure. This is very important even in this area of Industry 4. We are talking about autonomous system, automations. Failure becomes very critical, very important. Okay, now once we have looked into that, I will present you some statistics of system failures. It's a very interesting to see. If you look here, 60 to 70% of failure is due to the design and manufacturing. As I have been telling, like a designer introduces more than 50% and rest during manufacturing. But interesting is that operators, they also take its own share of more than 20 to 25% of the failure share. I remember when I was working in a mine, a machine hydraulic system was failing very frequently. Our deeper analysis, our interview analysis and our study revealed machine was okay, but it was failing due to the poor operation, due to the operator's failure. They were not knowing how to operate the system in a proper way. But very surprising, we also find even maintenance cause equipment to fail. If machine is working properly, we should not touch it. That's the old keep your hands off. Don't touch it. Because many times during maintenance you introduce error into the system. I will give you a simple example. Mostly this happens due to the human error. They forget to put a ring, oil ring, then your oil will be draining. They put a wrong parts, then it won't last. And this is so common. So whenever I leave my car for repair, I'm very careful when I take it back. I ask them many questions. One example I can give, that can be a human error example. But once I left my car for changing the deck, when I come out of the workshop, the bolts were not tightened properly. This is an error. Maintenance introduced error into my car. This can be a simple example, but you will find if you start analyzing your day-to-day work, you will find many times maintenance people do mistakes. And to control these mistakes, we have a checklist. Even then you will find some problem, and this is a big issue in airline industries. That's why it's a very regulated, very check is very hard there. You have to do the job, then you tick the box. Otherwise you miss some steps leading to catastrophic failure. Maybe I will be coming back to some example sometime. Yeah, we have seen failures. Now we'll define failure, the classes. Like there are two types, evident failures or hidden failure. Evident failure, as the word says, you can see it. It's a visible. The termination of an online or evident function is called evident failure. I see my car is running and suddenly car stops. I can see it, car is not running. That's evident failure. A failure that by itself becomes obvious to the crew or operator when they are performing their normal duties. Simple example as I told you. You are driving your car, car stops, you know that car has failed. What is hidden failure? Hidden failure, often you don't see what is happening. You are running your car, many times you don't know that engine oil is in a bad shape. The contamination of engine oil has become so bad that you should not run it. These are the hidden failure. It's not evident to you. So termination of the inability to perform an offline or hidden function is called a hidden failure. Failure that is not evident to the crew or operator while performing their normal duties. Perhaps I was wrong when I said the oil example, because when I'm doing maintenance, I can put my stick and see the oil is in bad shape. But I don't know about the some other failures, like my brake is not in really good, I can feel while braking. If my engine is not performing, if I hear some sound, I can recognize. But now in a complex machine, I don't have any idea. That particular component is not working, and these are hidden failures. And hidden failures are becoming really, really critical point of study by maintenance engineers and researchers. How to have track, because you don't see them, you don't hear them, you don't feel them until unless there is a sudden failure or gradual failure. So this has become a very, very important for us point of research in research world. Now we'll be looking into failure classification. Failure is classified into two broad groups: intermittent failures and extended failures. Intermittent failures are failures they are encountered and they correct themselves. The system corrects itself. Many times we don't know the reason, and this is not of interest for this lecture. We'll be focusing on extended failure. Extended failures can be broadly divided into two groups: potential failure and functional failure. We'll start looking first at potential failure. Potential failure can be classified into two groups. One is gradual failure, like system gradually migrates to a state which is almost working perfectly but not perfect. It is almost little deviation from the normal working conditions, and that happens due to degradation, wear out of the mechanical component, etc. So it's also called degraded failures. Second part of potential failure is the sudden failure. Suddenly a system goes to a lower state in a step way, and that is classified, or that is called sudden failures. Like a system jumps to a state that is not 100% perfect, but it is working perfectly, it is fulfilling the function, and that's a sudden failure. But our interest is in functional failure, so when system is not able to deliver the required function, and that can be gradual. How the system migrates from potential to functional failure, it's a gradual process. Slowly, gradually it migrates to functional failures, there we don't get the expected function from the system or item, etc. And second part is a sudden failures. Now that's very dangerous. That we don't want a sudden failure from an industrial system or from any assets, because that can be catastrophic. Just assume you are driving your car and your brake fails suddenly. You don't know anything about it. It will lead to accidents. Or you are flying. It's a really, and one of the engine doesn't work in the plane. If it is a two-engine plane, or if it's a single engine, it's a catastrophe. If it's a twin engine, it is still going to be a catastrophe. It's very, very dangerous, this sudden failure. And there are many ways. That's why to avoid, to protect, we have this what we call a standby system, etc. And the system is very, very critical from safety point of view. Now I will explain the concept of potential and functional failure using what we popularly call PF diagram. P stands for potential, F stands for functional failure. Look at this. X-axis is time, Y-axis is a performance, green line indicates 100% performance, and this blue line indicates the functional degradation of the components. What happens with time and with use? We get a deviation from the normal operation, and that is marked by, let's say, potential failure. This point is subjective in use. For different operation, this point can be here or this can be here, depending on the severity or criticality of the operation. If it is a nuclear power plant, I don't want much deviation. This warning should come here itself. Or if it is a something very day-to-day consumer applications, etc., with very marginal effect. This can be somewhere here. So this is a potential point, potential failure. That's like sorts of a warning, alarm that some deviation has started taking place in our operation or performance. Then most interesting is the functional failure. This red point indicates system will stop functioning or system will fail to deliver the required function, and then you must stop it. Similar to potential failure, this can be down, this can be here, depending on again the criticality and severity. Many times this is governed by the regulations, doesn't allow you to operate a system even though you are getting the function out of it. So you should be very careful. And using the concept of potential failure and functional failure, one can use a planning time horizon for maintenance. I get a potential here at time T1, I can call it, and I have this much time to plan my maintenance action. This is one of the important outcome of this PF diagram. Now we'll be looking into the failure severity. Failure severity can be classified into three broad classes: marginal, critical, and catastrophic. Now we'll look into marginal failure severity. This is defined as failures that result in minor injury or loss or simply irritation. Like there is no loss, there is nothing, but only you get irritated. And look at this photo or pictures, what I call. Clothes are hanging on a very roasted nail, and if something goes, if nail breaks, cloth will fall on the ground. It may get dirty again and you will be irritated. You have to wash it again. So this is a typical example I can show it to you. Next one is a critical severity, and critical severity is defined as a failures that may result in severe injury or major system damage. One example is a windshield wiper in a car. If it is not working and it is running heavily, it may lead to serious accident, and your visibility will be impaired. You will not be able to know where are you going. When you have to brake, you can't see the signals, and such small things can create serious accident. Similarly, poor brakes in car are example of can lead to critical, they are critical actually, they may lead to critical failure leading to accidents. So we should be careful. But when we come to the catastrophic example, failures that result in death or total system loss, often catastrophic failures lead to serious accidents. You lose the whole system, you lose the whole assets, or you lose the lives and all. This is an accidents, your aeroplane accidents, and these are not only loss of single life, often they are associated loss of several lives, maybe more than 100 of people die in such accidents, and we are aware about it. So this is a short example of failure severity. Now we'll get to I will show you some catastrophic consequences of such failures. And most critical one is a Bhopal gas disaster. This happened some 35 years ago, and still people are suffering from this. When it happened in India, this was a chemical plant disaster, and it happened due to the leak of methyl isocyanide gas from the plant, leading to at least minimum, people say more than 1 million people are affected. Still people are dying due to the impact of that gas leak. It says the statistics from the studies has shown that more than 100,000 people has got permanent health effects, lung and eye damages, lung cancers. So the effect of such disaster, such failure is still taking its toll. Why such disaster like Bhopal disaster do occur? What are the contributing factors to such events? One is undersized safety valves. You remember I said Design is one of the main important stages in ensuring failure-free operation. If designer fails to see the future, it fails to visualize the problem, he can use a system that is not sufficient. And Bhopal gas accidents or tragedy can be attributed due to undersized safety valves, or even management didn't have a very good maintenance routine. So we are talking about maintenance, and maintenance is very, very critical. You can not if you are not performing maintenance in proper way, it may lead to catastrophic failure, catastrophic accidents. And also some of the things like I was telling, like a context environment, you should not have, they should not have so much storage of the gas, but they had that. And dependence on manual operation. We just wish there was a artificial intelligence system or some condition monitoring that could have warned us that the system is going to fail. It was not there. It was 35 years ago, so systems were not available. Of course, management cannot wash its hand off from here because they had a poor safety management and inadequate emergency plan, leading to so many deaths and destructions in that area. Let us look into some other issues and other example. Alaska airline disasters. Why did it happen? The crash killed almost 83 people and crew, and contributing factors were extension of its lubrication interval. People wanted to save time in maintenance, so they extended the lubrication change interval on horizontal stabilizer that keeps the plane in stable conditions. Extended end plate check interval. They extend the interval, checking interval. That was very dangerous. And absence of the McDonnell Douglas MD80 of a fail-safe mechanism to prevent. So designer had no such mechanism. If somebody does a fail, if somebody extends, how can we compensate the loss in function? That was a design failure. Some more accidents in recent time. In 2000, there was a big accident in England. Loss of life was luckily very low. 4 or 5 people died. And that was attributed to failure of rail head fragmented as train passed. Extended head check interval. The maintenance contractor has extended the maintenance interval on that sections. That led to, they missed to see that there is a rolling contact fatigue. And investigation report found that rolling contact fatigue was the likely cause. Over 300, while checking, they found that there were 300 critical cracks on that area. So, what was the impact of this accident? The speed restriction and track replacement works caused significant disruption on majority of the national network for more than a year. More than a year, people has to suffer train delays, restricted speed, etc. So what I'm trying to say, catastrophic consequences of failures are not only that point of time. It can be 30 years, 40 years, 50 years, or can be at the best can be a year or so. So it's a very, very important to understand failures and its impact. And its most important consequence is the safety related, death and injury. That's very, very important. And of course, of late, lot more focus has been brought on environment. Many times we read that particular trawlers like a sea transport, tanker fails, tanker accidents leading to spillage of oil, that creates environmental problem. That is a very day-to-day, you can read into newspaper here and there. And of course operational, if train is running, suddenly train stops, you can be stranded for hours in a remote area without any support. That's very dangerous. Or your production loss, you can't produce the things you have planned, your customers are waiting. So this has a very, very operational consequence. Then we have also non-operational, like irritations, minor irritations, or something like not much loss, but you creates problem for other people and all. You can't be quantified, but it costs money at the end of the day. So failure consequences are many. And once we talked about these consequences, we would like to measure it. You want to know what does it mean in terms of quantitative terms. It's also worth knowing what is quantitative. How can quantitatively we can describe failure? Often failure is described by use of failure statistics from the past. Some of the measures are failure rate. People use failure rate to describe how fail safe is the system, depending on the failure rates. Mean time between failures is a very common measure of description of failure in a quantitative way. Failure density function or survival function, etc. Let's look what is failure rate. That's the most common description of failure in a day-to-day work. Failure rate is defined as 1 divided by mean time between failures. So there is an inverse relationship between failure rate and mean time between failures. Like higher the failure rates, you will have the lower the, and you will get the lower the mean time between failure rates. Now I will illustrate you some simple example how failure rate looks and how does it changes. Many times we have a failure rate which is constant, like I use some system and failure rate doesn't change with time, and this is very true for electronic components. Often when you will come to the next lectures, you'll see electronic components are memoryless, and what is failure rate today is the same after 5 years or 10 years. Good example is a television sets. You can buy a television sets, it can last for 20 years or it may fail in 2 hours. So that is mathematically described by a concept called constant failure rate or memoryless failure rate, etc. That's a constant. Then we have a decreasing failure rate. That's a very interesting area. You love to have a failures of an item that is reducing with time, and that is characterized by software failures. You know what you do when you use the software, you debug it so it becomes less failure with next hour, and that is a good example decreasing failure rate. But in day-to-day life, most of the mechanical system hardwares are characterized by increasing failure rates. I use my car, with age failure rate will increase. That's the reality. And in case of many systems except electronics, this is the common, that as we age, failure rate increases, and it is modeled by different types like increasing failure rate model, etc. We will be coming across this. We'll be discussing this with some examples in next lecture. Failure rate actions of service and maintenance. As I said you, like a car, as with time the failure rate increases. Many physical systems, with time the failure rate increases, and we as engineer, we as a common user, we want to control these failure rates, and maintenance facilitate this. By doing good maintenance, we try to reduce the failure rate, the intensity of failure, and this will be explained here with a very simple example. Let's look here. This is a normal failure rate of a system with no maintenance. So you will see, this is in the beginning when you bring a system into use. In the beginning it is higher, when you introduce especially in case of the complex industrial plants or complex machine, not your TV, not consumer goods, you don't want this. But most of the industrial systems, when you commission it, they have some failures, what we call like teething problems in the beginning, and gradually they become stabilized, and then they start working perfectly, and you have a design life indicated here by this gray zone, and then suddenly this wear out zone starts where failure rate is increasing. That's increasing failure rate. You can see It is gradually increasing. Then if I do a proper maintenance actions, what will happen? We'll increase this design life and we'll postpone this wear out zone. We'll postpone this increasing failure rate. We'll reduce the speed. So we get a more performance, more benefit out of this system, more useful life. So this zone, from zone this to this, is called useful life because we have much more focus on producing, taking the advantage of the system. And when we move out of this zone, then we need an intensive maintenance program to further reduce the failure rate so that we can have more benefit out of it. So this is, by proper maintenance you can reduce the failure rate and increase the design life. Now we'll summarize this topic of very interesting topic for failure. As a maintenance researcher, for me failure is my whole world, and often we say there is no option for failure. Here is, we don't talk about failure. You want to make it reliable, robust system, but every reliability literature, every reliability concept is dependent on understanding failure. So we have looked into this section, the basic concepts of failure, what is failure, how it works. We also looked into the different classifications of failure. We had some descriptions of quantitative descriptions about and qualitative descriptions, and of course we looked into the consequences. You remember Bhopal disasters and small accidents, etc. I will try to close this section with an old saying: for want of a nail a horseshoe was lost, for want of a horseshoe a horse went lame, for want of a horse a rider never got through, and for want of a rider a message was never delivered. For want of a message an army was never sent. For want of an army a battle was lost. For want of a battle a war was lost. For want of a war a kingdom fell. All for want of a care about a horseshoe nail. Remember, small things. Thank you.